Confidence interval example. We'll do an example similar to what you might see on the homework about how to find a confidence interval. Just as a reminder, we have these formulas that we'll use. So p hat plus or minus m is the formula we use to actually find the confidence interval, where p hat is our sample statistic, sample proportion, the estimate we get when we take a sample, and then m is our margin of error. We find that by multiplying z star times the standard error estimate, where z star we find in a table that you can find in the book, or I'm going to show you on this video, and then standard error estimate is given by this formula here. So just as a note, we use our standard error estimate. In other words, we use this formula with p hat instead of p usually because we don't typically know what p is. Okay, so when I said we're going to use a table to find z star, this is the table that we use to find z star. I'll show you how to use that in this video. Okay, so here's our example. In a simple random sample of 1,200 Americans aged 20 and over, the proportion with diabetes was found to be 11.5%, or as a proportion, 0.115. We will do parts A through D here. So we'll start with part A. Part A is, what is the standard error for the estimate of the proportion of all Americans aged 20 and over with diabetes? So to find the standard error, we use our standard error formula. So it's given by this equation here. Now, to use this formula, we need to know what p hat is and what n is. So n is always the number of people or things in your sample. So in this case, we're told we'd have a random sample of 1,200 Americans. And then p hat is the proportion who have some quality. And it's the proportion that comes from the sample, not the proportion that comes from the whole entire population. So P would be, like if we just did P without P hat, P would be the proportion of Americans in the US who have diabetes. P hat is the proportion we get from looking at just these 1,200 Americans who are in the sample. So we get some number out of 1,200 and we use that to calculate 0.115. Okay, so what do? We just plug them into this formula. So make sure you don't make a calculator error. You put 0.115 in the p hat spot, and then you do that on the top two numbers here, so here and here, and then you divide by 1,200. So make sure you do 1 minus p hat before you multiply 0.115. And then double check if you have your calculator on hand that you're getting this number. If not, you're probably making a calculator error. Okay. So part B, we're going to find the margin of error. So the margin of error is given by this formula here, z star times standard error. Now, standard error, we can use P to find standard error if we have P. In this problem, we don't know what P is. So instead of using standard error with P, we use standard error estimate like what we found in part A. So we need to find standard error estimate and z star. We found standard error estimate in part A, where we we don't have p again, so we used p hat to estimate it, and that was 0.0092. So we did that in the previous part. For z star, we're told we want a 95% confidence level. Now, that actually tells us what z star we use. In this case, we're going to use z star is 1.96. How do I know? I go to this table in the book, and it tells us what z star we should use for various confidence levels. So if we have a 90, we're told 95% confidence level, we go to 95% here, and then we go over and we use 1.96. Now, you can also use 2, but I'm pretty sure for most of the online homework, it assumes you're using 1.96. So I would try it with that. Okay, what do we do now? The formula says that we just need to multiply z star times standard error estimate. So we do 1.96 times 0.0092, and then we get a number. Now this is called our margin of error. Okay, part C. Once you have the margin of error, and you know what p hat is, then you can find a confidence interval. So we can find the 95% confidence interval using these two numbers. What do? We write down what the numbers are to make sure we use the right ones. So p hat and m we found, well, p hat is given, 0.115, and then m we found in part B. And then what we do is we take p hat, and then we both add and subtract the margin of error to get two different numbers. In other words, I'm going to take 0.115 and subtract it from and subtract 0.0180. And then I'm going to take 0.115 and add 0.0180. So you add and subtract the margin of error to p hat. Type those into your calculator and you end up getting 0.097 and 0.133. Now, we officially basically have the confidence interval now, but there's like different ways to write what it is. So a lot of people are going to say that our confidence interval is from 9.7% to 13.3%. So I've just converted both of these to percentages. So I moved the decimal 2 places to the right. You're also going to see your confidence interval written like this as an interval. So you might remember from algebra, you can write a range of numbers by putting like parentheses, one number, comma, the other number. And then you can do this in either decimal notation or percent notation. So a variety of ways to write your answer. Sorry, this thing down here keeps popping up. I can't get it to stop doing that. If I go too low with my cursor, it pops up. Okay, so we have our confidence interval expressed in 3 different ways. Now let's talk a bit about what this means. So part D will help us better understand that. Part D has a question. It says, according to the Centers for Disease Control and Prevention nationally, 10.7% of all Americans aged 20 or over have diabetes. Does the confidence interval you found in Part C support or refute this claim? Explain. So the question is, the CDC found, they did some study and they found 10.7% of Americans have diabetes. Did we find something that kind of like goes along with this? Now, to answer this question, we have to look at what our confidence interval is. So we found, when we did our study, that 11.5% of Americans over 20 have diabetes. And then we are confident at a level of 95% that this number, the interval over which we feel confident is 9.7% to 13.3%. So the idea is that we're 95% confident that the percentage of people with diabetes in the US that are over 20 is between 9.7% and 13.3% based on our finding of 11.5%. So the question is, if the CDC is saying that 10.7% of all Americans aged 20 or over have diabetes, does that make sense given what we found? So in this case, the answer is yes. And the reason is because 10.7%, it falls within this range of numbers. It's between 9.7 and 13.3. So it's not only close to these numbers, but it falls within this range of numbers. So we're going to say that it is plausible. It's a plausible value for the percentage of Americans to have diabetes. We think it's possible. Now, if the CDC had given us another number, for example, if the CDC had said that 8% of Americans have diabetes and our confidence interval was 9.7% to 13.3%, we would say that we think that's unlikely. We'd say 8% is implausible because it's not within this range of numbers. So we would want to do some more studies to try to determine what's going on here. So and just to like summarize, the idea is that your confidence interval gives you a range of numbers over which you think it's likely that some result falls, and then the confidence level, like 95%, 99% or whatever, tells us like how confident you are. And then just a note about this word implausible and plausible. It's not that it's impossible. So implausible doesn't mean impossible. It just means that we think it's like unlikely. So if CDC had come back with that number 8% and we said, oh man, 8% is not between 9.7 and 13.3, so we think that's implausible, we don't mean impossible. We just mean we would be surprised if that was true. Okay, so just a common misunderstanding really quick about how to interpret these. The right interpretation, if we're conducting our survey many times, is this. If we were to conduct our survey many times, 95% of our surveys would result in a confidence interval that includes the true population proportion. The wrong interpretation is there's a 95% chance that the population proportion is between 9.7% and 13.3%. Why is this second one the wrong way to interpret? Basically, it sort of like has to do with the exact meaning of what this phrase says. So like the true population proportion, it is only one value. So if you look at the whole proportion and like interview every single person in the US and find out like how many of them have diabetes, just of the people over 20 years old, that number doesn't change. There's just some set value for P. P hat can change depending on what sample you look at, but P hat never changes. So it's incorrect to phrase your interpretation in the second way because the second way is implying that 95% of the time P is between 9.7% and 13.3%, and 5% of the time it's not, but P actually never changes. It's not fluctuating. So, I mean, if you want to get super technical, you shouldn't phrase your interpretation the second way. You would want to phrase it something like the first way here. Okay, that's it for this video.